Hey everyone, I want to do a final video that sort of recaps the entire unit with a series of images and kind of annotating over some of the key points. First thing we talked about was vapor pressure and boiling point. And what I have here is a sample of molecules, and I'm going to go through each molecule to see what factors are involved here that would let me know, based on looking at its structure, what am I likely to see in terms of a vapor pressure and a boiling point. Now keep in mind, vapor pressure is just the willingness of a liquid to enter the gas phase. And the strength of a lot of its forces is going to play a factor into that. If you could imagine, these gas particles colliding with the walls of a container generates pressure. And so that's what we mean by vapor pressure. Typically, things with very high vapor pressure are going to have very low boiling points because they will readily enter the vapor phase without much trouble. Let's look at this first one. Okay, so I can see immediately, and one way to interpret this would be kind of, I know it shows OH, but that's just an O bonded to an H like that. And so you'd see the same thing with this one here. And so for the purpose of being consistent, I'm just going to show it like this. I have some features turned on this simulator that I just want to make aware of you right now. In organic chemistry, since these are organic molecules, there's kind of a system of drawing, and this is called bond line angles. And sometimes you don't have to show the carbons, but these H2 just lets you know there's two hydrogens bonded to this carbon, and then there's three hydrogens bonded onto this carbon. So when you look at something like this, it's probably going to have a pretty high molecular weight because we see 10 carbons here. I'm going to probably see some strong intermolecular forces for two reasons. One, I can see that I have hydrogen bonding, but the extra oxygen here is going to allow for this region of the molecule to be pretty polar. And so I could have an additional hydrogen bonding opportunity with the hydrogen of an opposite molecule of this. This is called decanoic acid, by the way. And this oxygen would be able to attract another hydrogen. So this one, it's going to have strong intermolecular forces. Check. It's also going to have a high molecular weight. Check. That happens here. Is it branched or could it have symmetry? Well, I'm going to say check first, and I'm going to show you why that would be. If I had this molecule, I'm never going to have just one. This linear shape allows it to stack relatively close to one another. And like I said before, this oxygen, a lone pair, could attract a hydrogen atom of another molecule. So it's going to have all three. So check. You're going to have everything with this. Probably has a really high boiling point, and for that reason, it's going to have a very low vapor pressure. It's going to take a lot of energy to get this to go from the liquid to gaseous phase. Moving along, I have something like this. Now, there is no electronegativity difference with anything here. Carbon and carbon is the same element. Carbon and hydrogen have an electronegativity difference of like less than 0.4. So you have all nonpolar bonds. You're only going to have London dispersion forces here. So it's not going to have strong intermolecular forces. Its molecular weight, yeah, I mean, there's 5 carbons, but that's still pretty low because carbon only has 12. And this branching and symmetry, has multiple branching points. And so it's likely that if you had more than one of these molecules, and you always would because I don't know how to isolate just one molecule, hey, how it copies there. This amount of branching causes something called steric strain. And what that means is another molecule is going to be floating around here, but there's all this stuff kind of floating around. It's unlikely to want to get close and be immediately repelled because you have all these branching points. So you're not really going to get a close packing of any kind of liquid molecules here because they're really just not going to be compatible with each other. So I have all three as a no for this molecule right here. Probably going to have a very low boiling point and a very high vapor pressure, but likely to go into the gaseous phase without too much trouble. I would say the same thing about this one here. However, this one might have a slightly higher boiling point than this one here because molecularly speaking, it has the same number of atoms and the same proportions, but its spatial arrangement is a little bit different. And so this is going to have a more linear shape, and you can have more stacking. So between these two that have nonpolar bonds, not an incredibly high molecular weight, no electronegative elements at all, low intermolecular forces. I would give the slight advantage to something like this that has a linear or more symmetrical shape to a branched chain like this. So I would imagine this one, which is just normal pentane, pent meaning 5, and that's for 5 carbons here. I would say this molecule here, probably going to have a low vapor pressure, but it might be a little bit lower than, say, something like this. It would probably have a low boiling point, but it would be higher than something like this. This thing, this is called dimethyl ether. I'm not going to get into it. You might see an increase in boiling point from this one, and the reason I say that is because you have an electronegative element. It might have a very slight polarity, so you might get some dipole-dipole forces with something like this. That's the one that I show here. This one is called ethanol. It's going to be more along this continuum, where, yeah, I have a lower molecular weight, but I've got hydrogen bonding, and I have a little bit of symmetry here with maybe another ethanol molecule. And finally, we just have, like, let's go with a control standard that you can reference. Usually water is in the discussion as a solvent because it's so ubiquitous, it's everywhere, it makes up most of our bodies and most of the Earth's surface for that matter. Okay, water, for something as small as it is, really low molecular weight, but it has some symmetry, sort of, in terms of it's not branching at all. It's a bent shape, which gives it high polarity, and it has a lot of hydrogen bonding. So those are the factors you want to consider. In a closed system, it's very simple. A substance will want to go from the liquid to vapor phase, but it will happen almost simultaneously, and that is the process of vaporizing and condensing. The vapor pressure in a closed system is very closely related to the movement or the temperature of the particles. Different liquids are going to exhibit different amounts of vapor pressure based on the things that we already talked about. Next, let's talk about solubility in water. We saw from a lab that the more carbons are added to an alcohol, the less energy is released in terms of it being an exothermic process, which we'll talk about enthalpy in a minute. Generally speaking, let's look at this as ethanol, and this down here is octanol, meaning 8, standing for 8 carbons. This region of the octanol molecule is incredibly nonpolar, and as this area grows larger and larger, it will be less and less compatible or soluble in water. It will have a hydrogen bond ability, but this large nonpolar section tends to repel polar molecules like water. If I was to have one nearby, if we can envision it occurring like this, a water molecule would be repelled by this large portion that is nonpolar. It would be slightly attracted to this region because we have, again, dipole-dipole and hydrogen bonding forces. But as that nonpolar region grows, it's going to repel polar molecules like water, and so we would see a decrease in solubility. Not discussed in class, but we've experienced before, are gases. Some gases are soluble in water, and some are more so than others. Example, nitrogen as a gas, N2, is not very soluble in water because the only force that's going to play here is going to be London dispersion forces. Let's envision this circle that I drew here, the polarizable electrons that could be influenced by water. That region is kind of small. Nitrogen is less electronegative than an element like oxygen, so the oscillations you could say with this particular electron that can move would be very slight, and so it wouldn't take much for nitrogen to just come right out of solution with water. Oxygen, a little bit more electronegative, and so it might, to a degree, have a little bit more solubility in water because it's going to have more electrons, and so we're going to envision that circle that I drew here is the polarizable section. Again, we can imagine oscillations between that electron cloud that kind of surrounds the oxygen, and because oxygen is electronegative, and there's a lot of electronegative elements in the water, like the oxygen, we can imagine these oscillations as being a little bit more prominent and more likely to momentarily attract another water. Lastly, you got something like ammonia. Now, ammonia has hydrogen bonding, where we didn't have that ability with these two other gases. So ammonia is very readily soluble in water. As soon as ammonia comes in contact with water, it has the tendency to want to enter the liquid phase and dissolve with water much easier because we have a lot more hydrogen bonding attractions that makes that energetically favorable. The solubility of a gas will generally decrease with water. For the most part, gas molecules don't attract very strongly to water, with the exception of ammonia being there. Keep in mind, as you increase temperature, you increase the oscillations of water. Here it is at a certain temperature. If I increase the temperature, we're just going to have a lot of this sort of back and forth oscillation. Easier to break, easier to set a gas free. Gas solubility also increases with pressure. This is called Henry's law, where the solubility of a gas is equal to its constant times the pressure of that gas. Moving right along, we discussed enthalpy of solutions, where an ionic compound can be dissolved in water. We think of this happening in three separate phases. The lattice energy of the solid must be broken. The hydrogen bonding from water molecules must be broken. And this hydration cell must be formed. This is typically referred to as the hydration of ions. And the more that these form, the more exothermic, because forming bonds is exothermic. This is a different kind of attraction. This is called the ion dipole force. It is a little bit stronger than just hydrogen bonding alone. It's where a formally charged particle has the ability to directionally orient water molecules a certain way. In the case of what we saw in lab, magnesium chloride, or certainly calcium chloride would do this. We have, some small atomic ionic radii, but chlorine has somewhat of a large atomic radius when it gains an electron. The space here is going to be influenced by the size of that ionic radius. Calcium chloride has a little more exothermic process because you have, of course, larger ionic radii and therefore a smaller lattice energy. Smaller energy needed to break these apart. What's important is that I have a different integer value in terms of charge. When 1 mole of magnesium chloride enters solution, you're actually going to get 2 moles of the chloride ion and 1 of the magnesium. Dissolving magnesium chloride in water would likely be slightly exothermic. The lattice energy and the energy needed to break apart water would be less than the energy formed, or less than the energy released when the new attractions formed. Something like magnesium oxide, probably not going to be very soluble in water, and if it was, you'd hardly notice it in terms of temperature changing, because breaking that lattice energy is going to be really, really difficult because we have smaller atomic radii, smaller ionic radii, and the spatial distance between ions gets smaller, so the lattice energy increases. Now, what we saw with something like a nitrate salt, this is ammonium nitrate, which we didn't have access to, but the size of that ionic radii become much larger, so the lattice energy of nitrate salt is going to be much lower than some metal and some halide or oxide ion. Now what happens here, this lattice energy is going to break apart very easily because you have pretty large ionic radii here. You have the ammonium ion, which is not even one element, it's a molecule on its own. And then you have the nitrate ion, which is not an element either. It's a collection of 4 different elements. When this forms bonds, in terms of the ion dipole forces, it will be less strong because the radii is larger. It was kind of like what I said earlier. This large radii kind of repels a lot of the charges, and so yes, it will attract momentarily the electronegative portion of water, but that attraction is not going to be as strong as something with a small atomic radii like the one shown here. Same with the nitrate, which is even going to be less, because one appropriate way to show nitrate through resonance would be the alternating double bond that you would see here. And that's going to give a partial 1/3 overall to all these oxygens, which is less of an attractive force to the partial positive region of this hydrogen. So yes, you're going to get some attraction, large ionic radii, and that decreased, let's say, attractiveness of the oxygen due to what's called a delocalized pi bond that alternates to all different oxygens. Is going to make that attractive force less. Something like dissolving ammonium nitrate in water would be endothermic because it's going to require more energy than the actual bonds that are formed, the attractions between a water molecule and one of those polyatomic ions. Lastly, an idea called entropy. There's many different definitions for this. The one that I prefer is disorder. Things tend to move in a more disorderly state, always, always. Things are constantly going from order to disorder. It's one of the unusual laws of the universe. If that could ever be reversed, it would be the most important discovery of all time. That I would guarantee you. What we did when we made solutions, let's say that this here represents an ionic crystal, and these represent water molecules. Here we see, with just focusing on this solid here, we see an area of more order, more symmetrical arrangement of components. That isn't going to last long. What's going to happen is that eventually entropy, and the abbreviation of entropy is just the letter S. E was already taken with energy and some other stuff. So when I put a piece of salt into a solution like water, over time it's going to want to favor disorder. And so these components that previously made up an ionic solid are going to like to disperse among water molecules. It is simply going from a high concentration to maybe a lower concentration, order to disorder. And so that is kind of the unit in a nutshell. So hope you found this informative. Keep in mind, here are those key themes: vapor pressure, boiling point, how to determine those two when looking at a molecule. What does it mean to be in equilibrium? What factors can influence the equilibrium? The solubility of certain substances in water, liquids versus gases, how the solubility of a gas maybe increases or decreases. Finally, we had enthalpy of solutions, which is oddly enough closely related to entropy. A ionic compound, when added to water, may either be exo or endothermic, and that's dependent upon how the lattice energy and how the formation of new attractions form. Larger, more higher in atomic radii compounds, usually polyatomic ionic compounds, are going to be endothermic when dissolved in water, particularly nitrates, which are very soluble. They're going to be endothermic because the bonds formed are not nearly as strong as what was required to remove them in the first place. Finally, we have this idea of when you make a solution, things tend to favor a disorderly state, and that is when you go from high order to less order. That is a law of the universe that happens pretty much with everything, not just solutions. Everything is going to go from an orderly state into a disorderly state. The fate of this universe will be a cold and dark one because all the stars eventually will run out of energy, and what we'd end up having is just a few photons kind of flying through empty space, probably in the very, very distant future. I'm sorry, that's going to be the way it is for now. So this was the unit of solutions and how they're represented, and some of the physical changes that are occurring with solutions, and we're going to introduce this idea a lot in further units. Thank you.